Welcome. In this lecture, we will introduce the concept of energy, and from that, we will define other quantities such as work, then the work energy theorem, kinetic energy, potential energy, and conservation of mechanical energy. First, energy. What is energy? Energy is simply the currency of the universe. It's somewhat of an abstract concept, but this is how we will think of it. Consider the universe to be like a universal bank, and there is a set amount of currency that the bank has, and it can distribute this throughout all of those inside the bank. Let's say I'm in the bank, or I'm in the universe, and I have some of this currency, which is the energy. I can take this energy that I have and give it to another object in the universe, or in this bank as we are using for our picture. And this currency, or energy, will be transferred from me to this other object, and as an example, I could use energy to lift the object. If I go and pick up a stone, I'm taking energy that's within me, that we'll say the universe has granted me, and I'm imparting it to the stone. Energy is measured in the units of joules. Now let's talk about the quantity known as work. As a reminder, in the previous chapter we discussed impulse. Now impulse is a force applied over a time interval. Work, we haven't defined yet mathematically, but it will be a force applied over a spatial interval, otherwise known as a distance or a displacement. So work is defined as energy transferred to or from a system via the application of a force along a displacement. And notice the italics. Along is very important, and you'll see why later. Let's consider these three different scenarios: a wall, a slope, and some stairs. If I have a ball, I lift the ball, I've done work. I've applied an upward force, and the ball has moved upward. I have done work on the ball. What about this situation? We have a ball at the bottom of a slope. I apply a force to the ball, directed up the slope, and the ball moves up the slope. Work is done. The third scenario, the ball is at the bottom of some stairs. I apply force on the ball and move the ball up the stairs. Work is done on the ball. Energy is imparted from me into the ball. I've transferred some of my currency to the ball. Now the ball has that currency, so to speak. What about this situation? This lifter is attempting to move the barbell. He's exerting a lot of energy. He's pulling up, but the barbell doesn't move up. Since the barbell does not move, even though he's applying a force, no work is done on the barbell. Even though he's expending energy, he's not actually imparting any of that energy into the barbell itself, so no work is done. And as a reminder, energy transferred to or from a system via the application of a force along a displacement is work, and that is represented mathematically as, well, W is the symbol we are going to use for work, which is why I didn't use W in the past for weight, because we want to reserve it here. Work, W, equals the force multiplied by the change in position, or the displacement. And you'll notice that work is a scalar quantity, and it's equal to the product of two vector quantities. So let's say we have a block, and a force is applied to the block, and that force moves the block, and it moves at a displacement of delta R. Now remember, work is related to the force applied in the same direction as the displacement of the object. So what we really want here is the component of the force parallel to the displacement. Now this brings us to this multiplication that we have in our equation, our definition for work. We see that work, this W, equals F dot delta R. Well, what is this dot? We have two vectors that are multiplied together and somehow they give a scalar quantity. Well, this dot is known as the dot product. And it's simply an algebraic operation that takes two vectors and returns a scalar. Let's set up a reference frame and let's draw the two components of the force in this reference frame. We have the vertical piece and we have the horizontal piece. And there is an angle that the force is at relative to our horizontal piece. And if we want the values of the components of this force, we use a little bit of trig, which I know trig is not required for this course, so I will try to explain all that I can to you, all that you need to know. The vertical piece of this force is simply the magnitude of the force multiplied by sine of that angle theta. And the horizontal piece is the magnitude of the force multiplied by the cosine of the angle theta. And why are we introducing these trig functions here? It's because our dot product can be written as shown right now. The magnitude of the force multiplied by the cosine of the angle theta, where theta is the angle between the displacement and the force vector, and then that is multiplied by the magnitude of the displacement. So again, this is the component of force along the displacement, and this is the magnitude of that displacement. But cosine is a function you may not have seen before, so let's go over some of the basic ideas of it. Cosine is this wave-like function. So cosine of theta versus theta. The origin is in its standard place, and let's talk about what happens when we plug specific values into cosine. So what is cosine of theta when theta, the angle, is 0 degrees? It corresponds to a value of 1. What does this mean? Well, this is the scenario where the force is perfectly in line with the displacement. What about cosine of 90? Cosine of 90 degrees is 0. If we look at the plot, we see the blue dot there. And this corresponds to a scenario where the force is 90 degrees to the displacement. Well, if cosine is part of our work definition, this means that if the force is perpendicular to the displacement, then cosine of the perpendicular angle of 90 degrees is 0, meaning the work done by this force in moving the object is 0. What about cosine of 180 degrees? That's -1. What situation does that correspond to? It's when the force is completely anti-parallel to the displacement vector. And what about cosine of 270? Well, that equals 0, and that is again a perpendicular angle, where the force is perpendicular to the displacement. So when the force is perfectly perpendicular to the direction of the displacement, no work is done on the object by that particular force. And cosine of 360 is just the same as cosine of 0, which equals 1, which we saw already above. Let's do a problem. Suppose that you apply a 60 Newton horizontal force to a 32 kilogram package, which pushes it 4 meters across a mailroom floor. Ignoring the friction between the package and the floor, how much work do you do on the package? Let's write out our givens. We have some applied force of 60 newtons. We have a mass of 32 kilograms, and we have a displacement of 4 meters. And the question is, what is the work done by the applied force? Let's separate this out to give us more room. Let's write out a reference frame and draw our forces on the object. And we know that we have the gravitational force down and the support force, or the normal force, up. And we are told that we have an applied force that's completely horizontal. And this applied force moves this object some displacement delta r, and we have the magnitude of that displacement being 4 meters as written in our givens. So the work done, if we refer to our definition, is simply F dot delta r. Remember, this is a scalar value and these two are vectors. Now the only force we're looking at here, the only force that has any component along the direction of the displacement, is our applied force. So we can rewrite this as F applied dotted with delta r. Reminder, this is the force that you apply to the box. Now remember that this dot product becomes F applied cosine theta delta r, where notice that no longer are these quantities vectors, they are now just values. So they're scalar quantities. The applied force, the magnitude of the applied force, multiplied by cosine of the angle between the force and the displacement, and then of course multiplied by the magnitude of that displacement. Now the angle between the applied force and the delta r is 0. They're in the same direction. So we have cosine of 0. Well, as we saw from a previous slide, cosine of 0 is identically 1. So this becomes 1. And now we simply plug in our values, 60 newtons, 4 meters, and we get a value of 240 joules. And this is our answer. Problem 2. Rank the situations in order of the work done by the force on the object from most positive to most negative. So here are the different situations. And our ranking will be on this line, this axis. So which one is the most positive here? So let's look carefully. Now, the one that will be the most positive is the one with the largest component of the force aligned with the displacement. If we look at A, this situation has the force completely perpendicular to the displacement, and therefore it probably will not be the largest. If we look at B, we see that the force is completely anti-parallel to the displacement, so that will yield a negative work. If we look at C, we see that the entirety of the force is parallel to the displacement vector. So we don't even have to look any further. That one will be the most positive work done on the block by the force F. What's the next most? Well, we see that there aren't any others of the remaining options of A, B, and D that have any component of the force in the direction of the displacement. So if we look at B and D, both of those have a component of their force anti-parallel, so some negative portion. Well, they will yield a negative work is what I mean to say. So that means A, since it will yield 0, is a greater value than what B and D would produce, because B and D will produce negative values of work. So we have C as the most positive, we have A as 0 work done on the block by this particular force, and now we have to look at B and D. Well, B has the force perfectly anti-parallel to the displacement vector, which means that it will be the most negative, and therefore we need to put D as our next option, and then B. Let's go to the work energy theorem. Now, bear with me, I'm going to write things out using calculus notation just to get to the end result. You don't need to know calculus, you just need to know how to use the end result once we get to it. Now, the full definition of work is a little bit uglier than what I showed you in a few slides ago. It involves an integral of the net force acting on an object or system multiplied by the infinitesimally small displacement. And we know by Newton's second law that the net force can be written as ma. And we know that a, the acceleration, is simply the change in the velocity over the change in time, which here I've written in calculus and notation. And I can move things around. And we know that dr over dt, that's just the change in the position over the change in time, which is the same as the velocity. And using some calculus rules, we can replace this dv dot v with 1/2 d of this v squared. And we can pull the 1/2 out, and evaluating this integral will yield 1/2 mvf squared minus 1/2 mvi squared, where we are finding the difference between some final value and the initial value. And this is the initial kinetic energy. This is a new quantity now, and this is the final kinetic energy. So we are calling these two things, final and initial kinetic energy. These are new quantities, but they are directly stemming from the definition of work. Now we can write this, it's the change of two things, or between two things. The final kinetic energy minus the initial kinetic energy. So how is this connected to the work energy theorem? Well, this actually is the work energy theorem. Work done on a system can change its state. Example, the kinetic energy. So we say that the work is equal to the change in kinetic energy. Now in the textbook, Conceptual Physics, instead of just writing K for kinetic energy, the author uses KE. I prefer not to use multiple symbols when we don't need to. Anyway, this result assumes mass is constant throughout the process. Let's talk about kinetic energy. We saw the equation for it, but let's be explicit and just put it on its own slide. What is kinetic energy? It's simply the energy of a system's motion. Typically, kinetic energy is associated with the macroscopic movement of a system, and kinetic energy is simply equal to 1/2 the mass of that system multiplied by its speed squared. Notice it's a scalar quantity, so kinetic energy is 0.5 the mass times the speed squared. An object must be moving to have kinetic energy. You can't have kinetic energy if you're not moving, so it is the energy of motion. The faster you're moving, the more kinetic energy you have. And again, if you're not moving at all, you don't have any kinetic energy. Another problem. An empty truck traveling at 10 kilometers per hour has kinetic energy. How much kinetic energy does it have when its speed is doubled? The options are the same, twice the initial, 4 times the initial, more than 4 times the initial. So what we're doing now is we're comparing the initial to the final, and we want to know how much greater or less than is the final relative to the initial. So let's write our definition of kinetic energy, and I'll put my subscripts here to indicate initial. So Ki, the initial kinetic energy, is 1/2 m times the initial speed squared. And we're told that the final speed is twice that of the initial speed. So our final kinetic energy will have different subscripts, and I'm using a different color here, and we're told if we plug in what our VF is, which is twice the initial speed, we know that we have now 1/2 m 2vi, all of which is squared. And if we take that square and you apply it to the 2 and to the vi, we get a 4. So that orange guy turns into a 4 because 2 squared is 4. And we have 1/2 mvi squared. 1/2 mvi squared is exactly the initial kinetic energy. And so we see that the final kinetic energy is equal to 4 times the initial kinetic energy. So if you double the speed of an object, you quadruple its kinetic energy. If you triple the speed of an object, the new kinetic energy is 9 times what it was initially. And you can see this because the speed is squared. So whatever value, whatever multiple you raise the speed by, you must square that multiple to see how much you raise the kinetic energy by. So the answer here is 4 times the initial. Let's talk about something else, potential energy. Well, this is going to be related to the work energy theorem. Now, the work energy theorem states that the total work done on a system changes its kinetic energy. So the total work done on a system equals the change in the kinetic energy of that system. Well, the total work can be split up into 2 parts. The work done by non-conservative forces plus the work done by conservative forces. What the heck are these? So work done by conservative forces. Well, what is a force that's considered to be conservative? Well, these are forces that, 1, depend only on the object's relative to position, and 2, whose work done is path independent. And I will talk a little bit about this in the following slides. Examples would be gravity, electrics, and spring forces. What about work done by non-conservative forces? Well, what is a non-conservative force? These are forces that are simply, well, not conservative. And this would be the bulk of forces. Friction, air resistance, etc. Anything that does not meet the criteria of being conservative. So almost everything else. If I push on an object, the force I apply is non-conservative. If I pull on an object, the force I apply is non-conservative. Friction, non-conservative. Air resistance, non-conservative. Almost everything is a non-conservative force. But conservative forces are very special, so it's useful to take a moment to treat them. What is an example of a conservative force? Well, we already talked about gravity, so what do I mean when I say a conservative force is path, or the work done by a conservative force is path independent? Well, let's take Earth, let's take a satellite, and let's say this satellite follows this weird path. Okay, so some work done is done by gravity on this satellite. What about if the satellite takes a different path? Just a straight line. Well, because gravity is a conservative force, the work done does not depend on the path. The total work done is the same regardless of the path you take. You can spiral all over the place, but the work done by the gravitational force will be the same. And this is different than a non-conservative force. For example, if I were to push on something, let's say a box across the floor, if I pushed it from one point to another in a straight line, I wouldn't have to do that much work. But if I push that same box in a zigzag pattern to get from one side of the room to the other, doing that pattern would require much more energy from me than just pushing it directly from one side of the room to the other. So my pushing is not a conservative force, unlike gravity, which is a conservative force. What does this mean for potential energy? Well, the work done by conservative forces, so we're considering work right now, and you'll see why, and forgive the calculus notation, we will get to the results that you need to know. Work done by conservative forces is simply the integral from the initial position to the final position of the conservative forces dotted with the displacement. And this produces a difference between this symbol here is U, which is going to represent, well, here we see this is going to be the initial potential energy, and this is the final potential energy. So here I'm using the symbol U. Now in your textbook, the textbook uses PE for potential energy. I think that's too many symbols, and I did not want to use P because P is already used for momentum and it will be used later for pressure. So I wanted to choose something that is found, well, Wikipedia has it for sure as U and sometimes V. And many textbooks use the convention of capital U to denote potential energy, and so I'm adopting that convention here. Now this is simply the difference from the final and the initial potential energies, and so what do we see is that the work done by conservative forces is equal to the negative of the change of the potential energy. But I've just been throwing terms around. What the heck is potential energy. Why is it called potential? Well, it's the potential of a system to do work. It's the energy stored and held in readiness, as your book states. So let's say I have a block and it's on a frictionless surface and there's a wall nearby, and I compress a spring between the block and the wall. The spring has the potential now, if let's say I'm holding the block, if I release the block, the spring will extend and shove the block forward. So the spring has potential energy. It has the potential to do work, to apply a force on the block and move the block in the direction of the force that the spring is applying. So it has the potential to do work on the block. That's why it's called potential energy. It's the potential to do something. It doesn't mean it's going to do something, but it means it's stored and ready to do something. So the spring potential energy, and we'll simply denote it as UI for initial. So let's say I release the block and boom, the spring extends, applying a force to the block, and the force, of course, is to the right, and the displacement is to the right. And so we see that work is done on the block because of the spring potential energy. So the change in the potential energy is related to the work done by the spring's force. Another example, let's say I have a physics book above a table, and it has some gravitational potential energy, which is the one we'll end up focusing in this class. So it has the potential to drop. If I release, let's say I'm holding the book. If I release the book, gravity is going to pull it down. So gravity has the potential to do work on this book if I release the book. So let's say I release it, and boom, it falls. And this gravitational potential energy we will define more explicitly because this is the one that we are going to focus on for this course. So gravitational potential energy. This is the potential energy a physical object with mass has in relation to another massive object due to the gravitational field. So if this is Earth, this is the Moon, there's some distance between them, there's potential energy because both of these objects are in the gravitational field of the other object. Let's give an example. Zoom into Earth a little bit. Let's say I have a little astronaut hovering in space. He has some mass. Let's draw a reference frame. And let's say that this astronaut is at some position, some vertical position y initial. And he has gravitational potential energy, which I'm defining for you right here for the first time in this lecture, as mg times that height. You might see it as mgh in the textbook, but I'm using y to denote height here. So the initial potential energy, the initial gravitational potential energy, is the mass multiplied by the gravitational field multiplied by the height, in this case relative to the surface of the Earth. And then the astronaut, let's say, moves further away, so he's at a new height of y sub f, the final y position, and he therefore has a new potential energy of mgyf. So this change in height produces a change in the gravitational potential energy. And again, commonly, you'll see y replaced by h, or even the whole delta y replaced by h. So the initial gravitational potential energy is mghi, the final gravitational potential energy is mghf, and the change in that gravitational potential energy is simply mg delta h, or, you could say that the starting point, you can define the origin of your reference frame to be the ground, the surface. So therefore, the initial height would just be 0. If you define the ground to be 0, then you just say, well, the change in potential energy is mgh. Example. An object with a mass of 20 kilograms is brought from a height of 2 meters up to a height of 6 meters. What is the change in potential energy? Let's draw a reference frame. Let's say I have a dumbbell. It starts at some height hi, and it's brought to some height hf. The change in gravitational potential energy is simply U sub f minus U sub I, which is simply mghf minus mghi. Mg is common between these two, so I factor it out, and now we just have the change in the vertical positions, which here I'm denoting by h, but you could use y or whatever symbol you want. Now I just plug in my values. 20 kilograms multiplied by 10 meters per second squared, because we are approximating the gravitational field near the surface of the Earth to be 10, as opposed to 9.8, and we multiply that by the difference of the vertical positions, 6 meters minus 2 meters. So the change in the potential energy, or the gravitational potential energy, is 800 joules. So we've increased the potential energy. The change in potential is positive here, which means this object now has a higher potential for gravity to do work on it. If you lift an object higher and higher, gravity has greater potential to pull it further down. So it has a greater potential to do gravitational work. Problem number 5. Change the wording a little bit. An object with a mass of 20 kilograms is brought from a height of 6 meters down to a height of 2 meters. What is the change in potential energy? Reference frame again. Now we start with a dumbbell high. So it's at some position, h sub I, and then it falls down. So we're not lifting it up this time, we're letting it fall down. So the change in the potential energy, same equation, plug in the same stuff, nothing's different with the equation. The only thing that's different is the values we put in. And this produces a negative 800 joules. This means now that our potential has decreased. We have a negative change. So we've gone from a high potential to a low potential. Because remember, when the object was high off the ground, there was a high potential for gravity to do work on the object. But now the object is close to the ground, and so the potential of gravity to do work has been lessened. So let's return to the work energy theorem, where we've split up our non-conservative and conservative work, and let's replace the conservative work with what we have found to be the change in the potential energy, or the negative change in the potential energy, because as we saw in a previous slide, the work done by non-conservative forces is equal to the negative change in the potential energy. And I can add that to the other side, and now we have the non-conservative work, or rather the work done by non-conservative forces, air resistance, friction, all that stuff, all the dissipative forces as we call them, equal to the change in the kinetic energy plus the change in the potential energy. Now this brings us to conservation of mechanical energy. What if we only have conservative forces acting on our system? What does that mean? It means that the work done by non-conservative forces must be zero. Well, the work done by non-conservative forces is on the left-hand side of this equation. But if there are no non-conservative forces, then that simply becomes zero. So what does this mean? It means that, well, zero equals the change in kinetic plus the change in potential. And that right-hand side, the change in kinetic plus the change in potential, is the change in the mechanical energy in total. Well, if the change in the mechanical energy is zero, it means that the mechanical energy is conserved throughout the process. And we can actually rewrite this equation as this, and you can choose whichever way you want to write it. They mean the same thing. One is just expanded and perhaps put in a more convenient form. Now this equation, this is the conservation of mechanical energy, which says that the initial and final total mechanical energies of a system are equal when there are no non-conservative forces acting on the system. So again, this can only be applied when there's no friction, there's no air resistance, I'm not pushing on something, you're not pulling on something. All that are present are conservative forces like gravity, which is what we've been mainly using. And so let's go over an example of that. Let's say we have this person standing on a really high, I don't know what this is, a diving platform perhaps. He's going to dive straight into a bucket of water. And let's assume there's no air drag. So that means the only force acting on this person will be gravity. So of course this is not realistic, but this is an idealized case. So this is essentially going to be free fall as soon as he jumps off. But at this position, he's at some height relative to the surface of the Earth. He has, let's say, for example, 10,000 joules of gravitational potential energy. But he's not moving, so his kinetic energy is zero, because you have to be moving in order to have kinetic energy. Well, what happens when he jumps? Well, he falls, so his height decreases. That means his gravitational potential energy decreases, but now he's moving, so whatever energy he lost in gravitational potential energy, he gained in kinetic energy. If he falls further, he loses more gravitational potential energy, but that gravitational potential energy is perfectly transferred into kinetic energy. Now he's moving even faster than he was before. And so on. The further he falls, or the closer he gets to the ground, which is the point of reference, the origin, the lower his gravitational potential energy becomes, but the greater the kinetic energy becomes. And when he gets all the way to the bottom, the gravitational potential energy has been perfectly transferred over to kinetic energy, which is the energy of motion. Now, this perfect transfer only works when mechanical energy is conserved. If air drag were present here, this would not be a perfect transfer. Some energy would be lost into the air, because this person would be running into air molecules, transferring some of his energy into the motion of those air molecules. So he would lose energy, it would be given off to the air molecules and making them move in ways they wouldn't have if he hadn't hit them. So in summary, we introduced the concept of energy being the universal currency of our universe, and from that, We talked about work, which again is the energy imparted to a system by a force along the displacement of that system. And we talked about the work energy theorem, which comes directly from the definition of work, where we assume the mass of our system remains constant. And the output of that work energy theorem was kinetic energy, where we said the work done, the total work done on a system equals the change in the kinetic energy. And then we introduced potential energy, which is really just related to the work done by conservative forces, where the work done by conservative forces is equal to the negative change in the potential energy, where so far in this course we have introduced specifically the gravitational potential energy with the formula mgh. And then we talked briefly about the conservation of mechanical energy, which is the situation when there are no dissipative forces, or otherwise said, no non-conservative forces acting on a system. I'll see you next time.